Today we're going to derive the famous reflection formula for the gamma function using only the integral definition of the gamma function, along with some powerful integration techniques, such as a change of variables in double integrals and contour integration. So our goal here is to show that gamma of z times gamma of 1 minus z is equal to pi over sine pi z. And like I said, we're only going to use the integral definition of the gamma function. That is, gamma of z is the integral from 0 to infinity of x to the z minus 1 e to the minus x dx. And here are our two tools. Here's a change of variables and integration tool for double integrals. Notice we pick up this thing right here, which is called the Jacobian. We'll calculate that when we get to it, for our particular case. And then this contour integral may be set up from complex analysis. Okay, so anyway, let's go ahead and dive in. We're simply going to start with the left-hand side here. So we've got gamma of z times gamma of 1 minus z. So the first trick here is to turn this into something that's a little bit more symmetric. And we can do that as follows. I'm going to multiply this by z over z, in other words, the number 1, and I'll take one of the z's into gamma of z and turn it into gamma of 1 plus z. So that's a standard characteristic that the gamma function has, which you can derive very easily using integration by parts right here. Okay, so now we have this thing that looks a little bit more symmetric. 1 over z, gamma 1 plus z, gamma 1 minus z. Now we're going to express both of those gamma functions as integrals. One an x integral and one a y integral. Okay, so this will be 1 over z. We've got the integral from 0 to infinity of x to the z e to the minus x dx. Because notice we've got this shift right here. And then likewise, here we'll have the integral from 0 to infinity of, let's see, this will be y to the minus z e to the minus y dy. Okay, so now let's push these together into a double integral. What will that look like? So I'll have 1 over z, and then the double integral, well, where both of the things are going from 0 to infinity, but I'll write that as the half open interval from 0 to infinity squared. So that's like the first quadrant. And then here we'll have x over y to the z. So let's write it like that. And then we'll have e to the minus x plus y. And then I'll have my differential area component right here. And then just looking at that integral, we've got a pretty big motivation for what our change of variables should be. And let's play around with our change of variables over here. So it stands to reason that perhaps x over y should be one of our new variables, and x plus y should be the other new variable, because those are playing important roles in this integral. So let's maybe set u equal to x over y, and we'll set v equal to x plus y. But now looking over here where we have our change of variables formula, notice we've got this partial of xy with respect to u, the term, but that means we need to solve this for x and y. There's actually a way around that, but we're not going to go over that here. We're going to do it in the most straightforward way possible. So how could we do this? Well, perhaps we could solve this thing for y. So you would have y equals x over u, plug that over here, and then you could solve for x. Likewise, you could solve for y fairly easily. And I won't do that, but what you end up with is x equals, let's see, we'll have u times v over 1 plus u. And then y equals, well, y is actually a little bit nicer. It'll be v over 1 plus u. And now let's calculate this object right here as a matrix. So maybe I'll write it. So we've got partial xy with respect to u, v. Okay, nice. So what will that be? So it's a matrix where the rows have to do with the functions x and y, and the columns have to do with derivatives of u and v. So right here we'll have the derivative of x with respect to u. So you can pretty easily calculate that. And you'll see that you get the following. You'll get v over 1 plus u quantity squared. And so you'll have to use the quotient rule there, but I think that's no problem. Then we'll take the derivative of x with respect to v for this entry. So that'll give us u over 1 plus u. And then here we'll have the same kind of thing, but for y. So the derivative of y with respect to u is fairly easily seen to be minus v over 1 plus u quantities squared. And the derivative of y with respect to v, which goes right here, will be 1 over 1 plus u. But now that's not exactly what we want. We want the determinant of that, well, and also the absolute value. So there's a little bit of a notational confusion here. Is this object the matrix or is it the determinant? Well, I'm not gonna really dip my toes into that, but what I will say is we need to take the determinant and the absolute value. Okay, so let's see. So I'll say this blue arrow here is taking the determinant of this object. And we'll have v over 1 plus u all squared. And you can see that because we build up to a 1 plus u quantity cubed in the denominator, but we've got a v plus u times v term, which after factoring a v out will cancel a 1 plus u in the denominator. Okay. So anyway, that's what we've got there. So now after our change of variables, our integral will look like this. So we'll have 1 over z, and then it'll be the integral from 0 to infinity, the integral from 0 to infinity. This is now a uv integral. It just turns out that this change of variables will take the first quadrant back to the first quadrant. And then we'll have x over y to the z, but that's going to be u to the power z. And then we'll have e to the minus x plus y, so that'll be e to the minus v. And then we'll have this object right here, which we calculated. And that's going to be, let's see, v over 1 plus u quantity squared du dv. But next up, we can split that into two integrals. And we can do this because the integrand is a function of u times a function of v. And notice our bounds of integration don't have to do with any of the variables. You know, the inner bound of integration could depend on, let's see, v in this case, but it doesn't for our purposes. Okay, so let's see, we'll have 1 over z, then the integral from 0 to infinity of v times e to the minus v dv, and then that'll be times the integral from 0 to infinity of u to the z over 1 plus u quantity squared du. Okay, so I think that's looking pretty good. Now let's focus on this first integral, which is the integral of v times e to the minus v, but that's pretty easy to calculate using integration by parts. Or you could notice that this simply is the gamma function evaluated at 2, which itself is 1 factorial, which is 1. So any way you look at that, that's just the number 1. Then we have our gamma of z times gamma of 1 minus z is 1 over z times that u integral. So let's start the next board with that. Okay, so on the last board we showed that gamma of z times gamma of 1 minus z was 1 over z times the integral from 0 to infinity of u to the z over 1 plus u quantity squared du. And now we're going to evaluate this integral using the methods of contour integration, but we've got to pick the right contour. So we want to look for where this function has poles. So it's pretty obvious that this function has a second order pole at -1. And that's because the denominator has a second order root when u is equal to -1. But then if z is not an integer, then u to the z is multi-valued. And since it's multi-valued, we generally take a branch cut along the positive real axis. So that means in order to set up our contour correctly, we should probably have -1 in the interior of the region just so that we can take a residue. And then we should also not include the positive real axis because we've got a branch cut along that positive real axis due to the way that u of z is built, or u to the z is built. So that gives us the following picture, which is known as a keyhole contour, and this is like a pretty classic keyhole contour. So let's see, we've got most of a circle of radius capital R, It just cuts right short at the real axis because again, we've got to like bring out or like cut out the real axis there. And then we've got this little bit of a bubble circle around here, which is around the origin. And around the origin again, because we've got to miss that positive or really non-negative real axis. And that's a bubble or a little circle of radius epsilon. Okay, so now before we get to calculating, let's maybe orient this the standard orientation, which is counterclockwise. So that means it's going like this. So, okay, so that's good. And now let's write all of these out. So let's see what's happening along C1. So that'll be the integral from epsilon to capital R. So epsilon to capital R of, well, just the same function. So u to the z over 1 plus u quantity squared du. Because that's the bit that's just above the real axis, or really like on the positive imaginary side of the real axis. Okay, good. And then let's see what's happening along C2. So maybe we'll write this down here. So along C2, what's happening? Well, u will be of the form r times e to the I theta. That's how you parameterize a circle of radius capital R. Notice that means that du is equal to I times r times e to the I theta d theta. And then furthermore, theta will go from 0 to 2 pi. So putting that all into our function will give us the following. So we'll have plus I'll put out front, and then the integral from 0 to 2 pi of, well, we'll have r to the z plus 1 times e to the I times z plus 1 theta d theta. And then this is going to be all over 1 plus r e to the I theta squared. And now this is the part where we're actually going to have to restrict the values of r that are maybe helpful. And that's because we want the power of r in the numerator here to be less than the power of r in the denominator. And notice the denominator is growing like r squared. So what does that mean? So that means we need the real part of z plus 1 to be less than 2. And if the real part of z plus 1 is less than 2, then as r goes to infinity, this whole thing is going to go to 0. That's because the denominator is going to dominate the numerator. So this goes to 0 as r goes to infinity, which we really want to happen. Okay, so now let's write what's happening on C3. So on C3, which is this bit of the real axis, which is like, you can think of as like being right below the real axis, or with tiny imaginary negative imaginary part. So in this case, you would replace u with e to the I 2 pi times u. That's because you're like rotating u around that real axis. Okay, so let's write what that would give us. So here we'll have plus the integral from r to epsilon, just based on the fact that we've got this orientation. And then we've got, let's see, e to the I 2 pi times z times u to the z over 1 plus u quantity squared. And that's because that's simply u to the first power, but there we've got this e to the I 2 pi, which is 1. So this is how we let this like take an effect, is where we've got this u to the z. And then what about du? Well, du will be simply e to the I 2 pi du upon this like simple change of variable. So that's not really going to contribute anything either. So there we've got du. Now next up, I'm going to take this, turn it into a minus sign, and change the order of the bounds of integration just to make it like kind of work with what we've got a little bit better. Now what do we have for this C4? Well, notice the C4 will be a circle of radius epsilon. So that's essentially what's going on right here. But it's oriented in the opposite direction. So we can set that up with a minus sign and then the integral from 0 to 2 pi of, well, it's going to be exactly this where we replace r with epsilon. So we've got epsilon to the z plus 1, and then e to the I z plus 1 times theta over, let's see, 1 plus epsilon e to the I theta all squared d theta. But now let's notice that regardless of what z is, as epsilon goes to 0, this whole thing will go to 0. So that's good too, because that's another integral which could be kind of gnarly that we won't really have to work with. So now let's notice what's left over is this bit right here and this bit right here. But those can be like very well combined, given that we've got the same bounds of integration. Okay, and then let's also, while we're at it, take the limit as epsilon goes to 0 and r goes to infinity. So that'll set this equal to, let's see, 1 minus e to the I 2 pi times z, because I can take that out of the second one as it's a constant. And then the integral from 0 up to infinity of u to the z over 1 plus u quantity squared du. Oh, but check it out. We have retrieved the integral that we really need. So perhaps we could solve for that integral that we really need, and then we'll only have to take this contour integral via the residue theorem. Okay, so let's notice that solving for that, we've got the integral from 0 to infinity of u to the z over 1 plus u quantity squared du is simply equal to 1 over 1 minus e to the I 2 pi times z times this contour integral over c of u to the z over 1 plus u quantity squared du. Now just hit both sides with 1 over z and we've retrieved this right here. Okay, so now let's maybe do the next step. So we just showed that our gamma of z times gamma of 1 minus z was 1 over z times 1 over 1 minus e to the I 2 pi z times this contour integral, where we chose this to be our contour. Notice that the only pole within this region that is bound by the contour is a second order pole at -1. So using the residue theorem, we know that this integral is simply 2 pi I times the residue of our function at that pole. So let's write that down. So this whole thing is 1 over z, and then we have 1 over 1 minus e to the I 2 pi z. And then after that, we'll have 2 pi I, so I'll put my 2 pi I here, and then the residue of u of z over 1 plus u squared at -1. But now, how do we calculate that residue? Well, we've got a nice formula for it, so let's recall that. I'm just going to copy most of this stuff down, so 1 minus e to the I 2 pi z. And then we'll have the limit as u goes to -1 of the derivative with respect to u of 1 minus u quantity squared times our function. So in the end, that'll give us our u to the z there. But now the derivative of this with respect to u is pretty easy. It's just z times u to the z minus 1. Okay, so now plugging u equals -1 into that will give us z times, well, -1 to the z minus 1. I'm going to write it like this. So we'll have 1 over z, and then 2 pi I over 1 minus e to the I 2 pi z. And then we'll have a z times -1 to the z, but I'll write that -1 as e to the I pi, so we have e to the I pi z times -1. So just to be clear where this came from, this is our -1 to the z term. Okay, great. So now let's get to a little bit of simplification. So this z here can cancel this z here. And then this -1 will flip that order of subtraction. And then we could maybe bring this into the denominator. So in the end, we'll have 2 pi I over e to the I pi z minus e to the minus I pi z. So that's after all of those simplifications that we just spoke about. Oh, but notice that's just the complex exponential version of the sine function where the reciprocal has been taken, and well, we've multiplied by pi. So that gives us pi over sine of pi times z. But check it out, that's exactly where we wanted to end. So thanks for sticking around. If you haven't subscribed yet, maybe consider subscribing. It would really help the channel out. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.